Hello, everyone. So in this video, I want to talk a little bit about translational and rotational equilibrium, and I'll do one application to biomechanics. So first, let's review what torques are and how to calculate a torque. So let's say I have this object called a rigid body. I'll just draw it out here. And let's assume that it's free to rotate about this point right here. So it's like pinned to the wall. So that point right there is called the axis of rotation. Let's say a force is applied to the object at some point on the object. I'll say right here. So I have a force F, right? It's a vector. And if you think about this, that force is going to cause this object to rotate about the axis of rotation, right? So in fact, it'll cause it to rotate, in this case, clockwise. So we can compute a quantity that describes the rotational ability of that force, and that's what's called a torque. So usually torques are denoted by the Greek letter tau, the torque here. And the way that you compute it is it's equal to plus or minus, I'll explain what that is in a second to get the correct sign. The magnitude of that force, I'll just call it F, right, with no vector on it. So magnitude of that force F times a special distance called the moment arm. So this L here is the moment arm. And the units, since it's a force, right, that's in newtons, if I use SI units, and the moment arm is a length, it's in meters. So the units of torque are Newton meters, okay, if we're using SI units. Okay, so what is this moment arm? How do I figure out this moment arm? Well, first of all, this force is acting along this line. So let me dash it in here in green. So this is called the line of action. Of that force. It's the line of action of the force. So the moment arm is defined to be the perpendicular distance from the line of action of the force to the axis of rotation. So notice here, if I go to the axis of rotation, there's many different distances to that line of action, right? So all these are distances to that line of action, but I want the one that's perpendicular. Basically, I want the smallest distance to that line of action from the axis of rotation. I want the perpendicular one. So in this case, let me do a different color here. Let's say this is the line of action. So I'll try and draw this in here. So it's perpendicular to, sorry, that's the moment arm, and it's perpendicular to the line of action of the force. So that's going to be my L. Okay, so in general, if I multiply the magnitude of F times that moment arm L, that's going to be the torque. Now, what about that sign plus or minus? Well, if that force tends to rotate the object counterclockwise, that's going to be positive. This is just convention. So we'll say the torque is positive if it rotates it counterclockwise. And it's negative if it tends to rotate the object clockwise. Okay, that's just convention. All right, what if we have a force and it's applied such that the line of action goes right through the axis of rotation? Let's say I have a force A here. And in this case, the line of action goes right through the axis of rotation. And I want to compute the torque due to that force A, the torque due to A. Well, if you think about this, right, there's definitely a force there. So I have the magnitude of A, however many newtons that is. But in this case, see how the moment arm is going to be 0 because the line of action is going right through. So if I look at the distance from the axis of rotation to the line of action, there's basically no distance there, right? So that moment arm is 0. And that's going to give me a torque of 0 Newton meters. So whenever you have a force where the line of action passes through the axis of rotation, however it's drawn, it could be like this, right, where it passes through the axis of rotation, it's not going to contribute a torque about that axis of rotation. Right, so in this case, there's definitely a force there, A, but it doesn't contribute a torque about that point of rotation. Okay, now having said all this, and I really like to use the moment arm when I calculate torques, but there are other ways that you can do this. Let me just quickly show you like two equivalent ways of calculating torque. So one of them is just what we talked about, the moment arm. Here, I'm going to draw a new picture. Let's say this is my axis of rotation. Here is sort of like the radius that goes out to the force. This is the applied force. We'll call it F. And it's applied at some angle. Say theta. Okay, so I'll call this R and call the F. All right, so I want to calculate the torque due to that force F about this point, about this axis of rotation. So one way of doing it is exactly what I just explained, right? I can find the line of action of this force. So that's the line along which the force acts, like this. And then if I want to find the moment arm, I need to find the perpendicular distance from the line of action of the force to the axis of rotation, which is this distance right here. Right, that's the one that's perpendicular to the line of action, right? From the axis of rotation, perpendicular to the line of action of the force. So that's my little L. So the torque is going to be equal to, first of all, if that force were really pulling on an object like that, in this case, it would rotate it counterclockwise, right? So if you were to pull up like this, it would rotate this whole thing counterclockwise. So that's going to be, by definition, a positive torque. And it's going to be the magnitude of F times the moment arm. But in this case, this moment arm, right? This angle right here is also going to be theta, because these are vertical angles, right? They're equal. These angles are equal. And then to figure out this moment arm here, well, I know that if you think about it, you have a right triangle here. Let me draw this one more time. So I have a right triangle. This angle is theta. This is R, and I'm looking for L. So relative to that angle theta, the L is opposite and the R is the hypotenuse, right? So what trig function relates opposite and hypotenuse? That's sine. So basically I can say sine of theta is equal to opposite L over R. And if I multiply both sides by R, I can rewrite L as R sine theta. So really this torque you could write as it's plus F, and then the L there is R sine theta. Okay, usually you compute the L separately, you just get a number and then you can say it's F times L. But if you're using this entire radius, so that goes from the axis of rotation to where the force is applied itself, then this L right here is always going to be R times sine of that angle. Okay, so that's the way we explained it. That's the way I usually do it when I teach torques. However, another way of computing the torque is instead of finding this moment arm, you can use the entire radial distance here, this entire R, and you can resolve this force into components that are perpendicular to this radial distance and parallel to the radial distance. So let me show you that quick on the next page. So I'm going to draw the same picture. So here's my force. This was R. and this was theta. And now I'm going to resolve that. I'm going to find the components of that force that are parallel to that radial line, which if I project onto that radial line like this, then this is going to be the parallel component. I'll call it like F parallel. And then I'm going to also project it onto perpendicular to that radial line. So I'm going to project it onto the direction that's perpendicular. So I'm going to call that F perpendicular. Okay, and if you notice here, right, if you're going to calculate F perpendicular, which is really the same as this length right here, so this F perpendicular is really the same as this, which again, I have a right triangle here. So this is F perpendicular, this is F parallel. And if I want F perpendicular, since F perpendicular is opposite of the angle theta and F is the hypotenuse, again, I need to use sine. So I know sine of theta equals F perpendicular over F. So that means F perpendicular is F sine theta. And then if you really wanted to find F parallel would be F times cosine of theta. Okay, so now when I look at the torques, right? So I want to find the torque of both of those forces. So basically I want to find the torque of F parallel plus the torque of F perpendicular, right? About this point of rotation. But notice here, F parallel, this one, its line of action goes right through the axis of rotation. So F parallel will never contribute a torque, right? So the torque due to F parallel is going to be 0. That's 0. So the torque is really only due to the component of the force that's perpendicular. So in this case, this torque is going to be equal to F perpendicular times its moment arm, but its moment arm in this case, right, if this is the line of action, the perpendicular distance is just this distance. It's the entire R here now, right? Because that's perpendicular to F perpendicular. So that's the entire distance R. So this is going to be F perpendicular times R. And again, it would cause it to rotate counterclockwise, so it's going to be positive. But remember, F perpendicular, we just found over here, is F sine theta, right? So this torque is equal to plus F sine theta times R. And notice that this is exactly the same equation that we got earlier, right? So this sine of theta, either it's combined with the F to give you F perpendicular times R, or if you look at the first page, the sine theta is combined with the R to give you the L. So you're either using like the full force times part of this radial length, just the moment arm, right, R sine theta, or you're using the full moment arm, R, and times part of the force, which is F sine theta. But either way, you get the same exact equation, okay? I usually like to do it this way using moment arms. And when I do the one example, I'll do it with moment arms. All right, so let's go ahead and do one application. So in this problem, you're told a 242-pound patient is standing with the glenohumeral joint abducted to 90 degrees. I'll draw this picture in a second. So that the upper limb is parallel to the floor. Assume that the total upper limb is 5% of the total body weight, and the center of mass for the limb is 29 centimeters from the axis of rotation. The limb is kept in place by an isometric contraction of the deltoid muscle. The muscle is inserted at a 10-degree angle at a distance of 19 centimeters from the axis of rotation. There is no weight in the patient's hand, okay? And we want to solve for the magnitude of the deltoid muscle force and also the joint reaction force at the shoulder joint, right, in newtons. And then ultimately we want to give the percent of body weight of each of those forces, right? The muscle force and then the joint reaction force. Okay, so the way I would start this is let's start by computing the values that we need in the correct units. So we're given that the weight of the person is 242 pounds, but I want to put that into newtons, right? So I know that 4.4488 newtons is 1 pound. So if I take this value in pounds and I use a unit conversion factor, I multiply by 4.4488 newtons per 1 pound. And I wrote it that way where pounds are in the denominator, so they cancel. I'm going to get 1076.6 newtons. Okay, you could probably round to 1077. That would be fine. And then the weight of the arm itself, the entire upper arm, forearm, and hand is going to be 5% of the body weight. So we're told that the weight of the arm is 5% of the total body weight. So, well, 5% of the body weight, you can write that as 0.05 times the body weight, right? Times 1076.6 newtons. And that ends up being 53.8 newtons. Okay, let's draw this out. Let's draw out the situation here. So I have, here's the shoulder joint. I'm just going to draw this as a stick figure. I'm not really good at drawing, so let's say this is the upper arm, forearm, and hand, so the entire arm held out at 90 degrees, right? Because it's abducted to 90 degrees. And we know that the weight of the forearm and hand and upper arm, right, the whole thing, is going to act at the center of mass of that entire limb. So we're going to say the center of mass is, say, like right here where that X is. So that's the center of mass. So again, what's going to act there? That's going to be the weight of the arm. And it's really a vector, right, acting downward. We also know that the muscle force is acting at a certain distance away. I'll draw on the distance in a second. And it's pulling at an angle, so I can like this, of 10 degrees, right? So this is the muscle force. I'll call it Fm. Again, it's a vector. And then this angle here is 10 degrees. And we also have a joint force that's acting at the shoulder joint, right? So that's going to be a joint force. I'll just draw it like this, where both components are positive. So we'll call it Fj. Okay, what else do we know? We know these distances, right? We know that the distance from the shoulder joint to the center of mass of the entire arm, so this distance right here, this is going to be 29 centimeters, but then I want meters, right? 29 centimeters. So that's going to be 0.29 meters. And then the distance that the tendon from the muscle, where it attaches relative to the shoulder joint, is 19 centimeters. So this right here would be 19 centimeters, which is 0.19 meters. Okay, I need to find the torques, right, due to every force here. And I know that this is what we're going to use. If the arm is in rotational equilibrium, which means if you're just holding it there, right, you're doing an isometric contraction, that means that the entire arm is in rotational equilibrium. If an object is in rotational equilibrium, that means that the sum of the torques about any point that you want to choose as your axis of rotation to calculate them about has to equal 0. And we're going to choose the shoulder joint as our axis of rotation. So the sum of the torques has to equal 0. Okay. So in order to calculate torques, remember torque is equal to plus or minus a force times the moment arm. We need to figure out all the moment arms. Well, the weight of the arm, this one's easy, right? Because this is the line of action of that force because it acts straight down. So the perpendicular distance from the line of action of the force to the axis of rotation is just this distance. Right? So the moment arm for the weight of the arm is simply going to be 0.29 meters. Okay, I'll call this L2. So like L2 here is 0.29 meters. That is the moment arm for the weight of the arm. What about the muscle force? Well, the muscle force, this is the line of action, right? That's the line along which that muscle acts. So the moment arm is going to be the perpendicular distance from the line of action of the force to the axis of rotation. So in this case, it's going to be this distance, the one that's perpendicular. So I'm going to call this, I think I called it L1 in my notes. Call it L1. So this is L1. That's the moment arm for the muscle force. Okay, so how do I calculate that L1? Well, I know I have a right triangle here, right? That I can extract. Let's actually just draw that somewhere else. Let me draw that right triangle. So I'm looking for this distance, L1, and I know this distance is 0.19, right, meters, and I know this angle is 10 degrees. So using trig, right, relative to the 10 degrees, what is the L1? Well, that's opposite, right? And in the 0.19, in this case, it's the longest side, it's the opposite the right angle. This is the hypotenuse. So what trig function relates opposite and hypotenuse? That's sine. So I know that sine of 10 is equal to L1 over 0.19. So therefore, L1 is going to be 0.19. I'm basically just multiplying both sides now by 0.19. Right, those cancel. So it's 0.19 times sine of 10 degrees. So if you work that out, this is going to be like 0.033 meters, right? So a pretty small distance because it's really, the muscle is really pulling at a very small angle, right? So that's going to be a small distance there. Okay, now that we have the moment arms, oh, and by the way, there is one more. The joint force itself, this passes right through the axis of rotation. So the joint force has no moment arm, right? Its moment arm is 0. Okay. All right, so now I can do the sum of the torques. So I have 3 forces. Let me do 3 torques, right? Each force is going to contribute a torque. They might be 0, but I'm going to write them down anyways. So I have a torque due to Fm, the muscle force, plus a torque due to the weight of the arm, plus a torque due to the joint force. That's got to equal 0, right? The sum of the torques has to equal 0. And we just said that that joint force, so this one right here, since it passes right through the elbow, the shoulder joint, there is no moment arm, right? So that torque, since torque is force times moment arm, that torque is going to be 0, right? There is no torque due to the joint force. But the other two will have torques. So the torque due to the muscle force, well, it's going to be the muscle force, Fm, times the moment arm, which we just said was L1. And then we have to think about this. Well, if that were the only force acting, how would it rotate the arm about the shoulder joint? Well, it would pull it so that it rotates counterclockwise, right? So that's going to be a positive torque. This is positive. And then the torque due to the weight of the arm is going to be the weight of the arm, that's the force, times the moment arm, which was L2. And if that were the only force acting, how would it rotate the arm here about the shoulder joint? It would rotate it clockwise. So that's going to be a negative torque, and that's got to equal 0. And now notice I can solve this for the muscle force, which is what I want, right? I can solve this for Fm. So if I solve this for Fm, I'm going to add this term to both sides. And then divide by L1. So Fm is going to be the weight of the arm times L2 divided by L1. And then I can plug in, right? So I know the weight of the arm was 53.8. L2 was 0.29. And then L1 was 0.033. And that's going to give 472.8 newtons. Okay, so that's the muscle force, right? That's the deltoid muscle force in order to hold the arm in that position, abducted at 90 degrees. Okay, now we want to find the joint force, right? The magnitude of that joint force. So I'm going to draw the picture again. Here's my shoulder joint. There's the upper arm, the entire arm, upper arm, forearm, and hand, held at 90 degrees, abducted. Then I have the forces acting here, so I have the weight of the arm. And then I have the muscle force. And this is acting at 10 degrees. And then I also have the joint force. And I'm going to draw the joint force. You can draw it however you want. I'm going to assume that the X and Y components of the joint force are positive. So that's why I'm drawing it like going into the first quadrant. This is a joint force. So now we want to come up with, we want to calculate what that joint force is. So here's where, remember we said that if you're just holding it doing an isometric contraction, holding your arm abducted at 90 degrees, it's in rotational equilibrium. It's also not accelerating in the X and Y direction, so it's also in translational equilibrium, which means that the sum of the forces, and I'm going to write this as, I'll break it up into its components. The sum of the forces in the X direction must equal 0, and the sum of the forces in the Y direction must equal 0. Why? Because it's in translational equilibrium. It's not accelerating to the right or left, or up or down, right, in either the X or Y direction. So the acceleration in the X and Y directions are 0. So the sum of the forces must be 0. So that's what we're going to use to figure out Fj. So what I need to do here is I need to find the components of each of those forces, right? So if this is my standard coordinate system, I'm just going to use X going to the right and Y going vertical. I want to find the X and Y components of each of those forces. So let me start with the muscle force. I'll draw it here. So this is 10 degrees. I want to project it onto the x-axis. So I want to find this x component, which I'll call like fmx. And I want to project it onto the y-axis and find this component, which is like fmy. Okay, well, again, if you think about this, right, I can extract a right triangle that contains that angle that's really the reference angle. I know the magnitude of Fm. We just calculated that, right? That was the deltoid muscle force. It's 472.8 newtons. I know this angle, 10 degrees. I want to find Fmx, Fmy. So again, let's start with x, the x component. This is adjacent to the angle 10 degrees, right? And the 472.8 is our hypotenuse. So I need to use the cosine function. And then to find the y, I need to use sine. Okay, so I know Fmx is going to be 472.8 times cosine of 10 degrees. But we have to be careful, right? I need to attach the correct SIG in now. And I know that that component, since it's going to the left, is going to be negative. So this will be negative. And if you work this out, this is negative 465.6 newtons. And then for the y component, it's going to be 472.8, 472.8 times sine of 10 degrees, and that is positive. Okay, and if you work that out, it turns out it's like 82.1 newtons. All right, what about the joint force? Well, we don't know the joint force, but I assumed, I'll just draw it here. I assumed it was acting in the first quadrant, which means that the x component we're going to assume is positive, and the y component we're going to assume is positive. And you're free to do that. You're free to draw. It's unknown. You're free to draw it however you want. And then when we calculate it, if we get a positive answer for fj x, then we know that it actually was positive. If we get negative, we knew it was actually going the opposite way, right? So we can like correct that later. And then the weight is really easy. For the weight, it's acting straight down. So this is the weight of the arm. So because it's acting straight down, right, it has no component. That vector has no component in the x direction. So WAX is going to be 0. But then WAY, the entire thing is acting in the y direction, but it's negative, right? So it's negative, and what was weight of the arm? 53.8, I think. Newtons. Okay. So now that I have all the components, I can actually sum the forces. So now if I'll do sum of the forces in the x is equal to 0, and then sum of the forces in the y is equal to 0. So in the x direction, I have the x component of the joint force plus the x component of the muscle force plus the x component of the weight of the arm. That's got to equal 0. So the x component of the joint force, that's what we're looking for. So that's just fjx. The x component of the muscle force was here, right? So fmx, and it was negative 465.6. So this will be negative 465.6. And then the x component of the weight of the arm was 0, right? There was no x component, so that's 0 is equal to 0. And if I add 465.6 to both sides, I'm going to find that the x component of the joint force is 465.6. Do the same thing for the y direction. So I have fjy, the y component of the joint force, plus fmy plus way is equal to 0. So I have fjy. Fmy is going to be positive 82.1. Right, we calculated that earlier. Fmy is positive 82.1. So plus 82.1. And then way was the weight of the arm. Remember, it was all acting downward. That's over here. And it was negative, right? Negative 53.8. So this is minus 53.8 is equal to 0. So then if you solve this, I can combine those. So 82.1 minus 53.8 is going to be 28.3 equal to 0. And if I bring that to the other side, I'm going to have fjy is equal to negative 28.3. Okay, so remember I assumed that fjy was positive, and in this case, when I actually calculate, I get a negative answer. That means the y component was actually pointing downward. So now we can actually find, because ultimately we want to find the magnitude of that joint force, right? So I'm going to go on one more page here. Remember that fjx was 465.6. fjy was negative 28.3. So if I draw this out, it looks like the joint force is going to be actually pointing like in the fourth quadrant. Right? So FJX is positive. This is 465.6. And then FJY was negative 28.3 newtons. So the actual vector, Fj, it's got to be in that fourth quadrant like this. So this is Fj. And it's at some angle theta here. Okay, so what I need to do is I need to find the magnitude of that vector. Well, again, if I extract this right triangle that contains the reference angle, so I'm extracting this triangle right here. This is theta. I'm looking for Fj. I know this distance is 465.6. And I know this distance, even though it's negative, right now I'm just drawing as a triangle, so it's just a length, so I can write positive 28.3. And then how do I figure out Fj? That's where you use Pythagorean theorem. So Fj is going to be equal to square root of 465.6 squared plus 28.3 squared. Right? A squared plus B squared equals C squared, where C in this case is my joint force. It's the hypotenuse. So if I take the square root of both sides, that should give me the answer. And if you do this, you're going to get 466.5 newtons. Now, they didn't ask for the angle, but we could also get the angle there by using inverse tangent. So this angle theta is going to be the inverse tangent of opposite over adjacent. So 28.3 over 465.6. And that turns out to be 3.48 degrees. But because it's in the fourth quadrant, you have to give more information. So we would just say like south of east. Okay. Or if you wanted to, you could give this angle that goes from the positive x counterclockwise to that vector, but then you would just subtract it from 360 degrees. So it'd be like whatever that is, 356.52 or something. Okay, but you can say 3.48 degrees as long as you say south of east, so you know that it's in that quadrant. Okay, and then the last thing we wanted to do was we just wanted to represent all those values now as a percentage of body weight. Okay, so remember FM was 472.8 newtons. And if I want FM as a percentage of body weight, then I would take my FM value, right, my muscle force, the deltoid muscle force, divided by the body weight, the total body weight, W, and then multiplying it by 100 just converts that ratio into a percentage. So in this case, it'd be 472.8 newtons divided by, what was the body weight? 1,076.6 newtons, and times 100, I'm going to get around 43.9%. And then for the joint force, right, we found the joint force was 466.5 newtons. So if I want the joint force, Fj, as a percentage of body weight, then I would do the same thing. Actually, it looks like they're going to be close, right? In this case, the percentages. I would take the joint force, divide by the total body weight times 100. So in this case, it'd be 466.5 divided by 1,076.6 times 100. These are both really newtons, right? But those newtons will cancel. I'm going to get 43.3%. Okay, so hopefully that helped. I did do it using moment arms. The other way of doing it is you could resolve the muscle force into a parallel and perpendicular component, and you'll get exactly the same answer. Okay, if someone's interested, you can ask me, and I can do another video on that if you need me to. All right, hopefully that was helpful. Thanks.